let's talk about thermal equilibrium and heat transfer. And this just kind of follows up with what we were talking about last time. We were talking about temperature last time, but now we're going to talk about how the temperature changes and what happens when the temperature of a material, a gas, liquid, or solid, what's happening when the temperature is changing. Let's have a container of, let's just say it's hot water. We have a container of hot water, and we're going to put it right next to a container of cold water. So this will be hot, and this will be cold, as measured by a thermometer. And then we're going to put, these containers are right next to each other, but then we're going to seal them up in an insulator. So this is an insulator. Now, what does an insulator do? Well, what does an ice chest do? You put stuff in an ice chest, it's just an insulator. Well, what it does is it prevents thermal energy from getting in or getting out. So thermal energy cannot be transferred in or out. This just isolates these two containers, this hot container and this cold container. It just isolates them from the rest of the universe. We'll talk a little bit more about that. Now, what makes the molecules in the hot container different than the molecules in the cold container of water? Well, if I draw a few water molecules, just a representative sampling, and I do the same thing over here, these molecules are at a higher temperature, which means that they're moving at a faster speed on average. So this one's moving really fast, and this one's moving this way. Now, it's all in random directions, and some of them might be moving, faster than others, and they bounce off the walls. They ricochet off each other. So these are really moving, though. These are hot. Now, by the way, it's these ricochets off the walls that give it pressure, okay? And if this was a gas, then the faster they're moving, the faster they're hitting the container, the more pressure they have. Now, these molecules of water are cold, and it's the same stuff, it's still water, but what's happening here is that the average speed is much slower. Okay. And this is the only difference between stuff that's hot and stuff that's cold, is the average kinetic energy of the, it's related to the average kinetic energy of the molecules in the material. Now, here's an example of this. Same situation, except it's not insulated. This is my my coffee. Whoa, that's big coffee. Let's raise this up and zoom out. So here's my cup of coffee. Okay, now it's still pretty hot. It's still pretty hot, but what's going to happen to my coffee, to the temperature of my coffee, if I don't drink it soon enough? Is it going to stay the same? Is the temperature going to stay the same? No. It's going to slowly decrease in temperature until it reaches what temperature? The temperature of the environment, the room. Now, what is the temperature in here? Look at right, 72? So it's 72 degrees. So I guarantee if I leave this out, in about 20 minutes, 30 minutes, my coffee is going to be 72 degrees. So its average kinetic energy is going to drop. Now, where did that energy go? It went into the average kinetic energy of the environment. But the environment is so big that we don't really feel as any significant temperature change in the room because my coffee's cooling off. But nevertheless, that will happen. Now, in this case, if I stick a thermometer in here and I say, oh, this is 90 degrees Celsius, that's really hot. and I stick a thermometer in here, and I say, oh, this is 3 degrees Celsius, very cold water, uncomfortably cold. Okay, zoom back in. Okay, now, if I leave this for a long enough time, let's say I leave this and I come back in a couple of hours, what's going to happen to the temperature of the hot water? It's going to drop. What's going to happen to the temperature of the cold water? It's going to increase. And that will continue until what happens? Yeah, the temperature will become the same temperature. Both the hot stuff will cool, the cool stuff will warm until they reach the same bland temperature, till they reach what's called thermal equilibrium. Now, what's going on? Why is this happening? Well, think about at the level of the atom, but remember, there are countless numbers of them. You could spend your whole life counting all the atoms or all the molecules in this container, and you won't even reach a small fraction of them. If you counted 1 a second for your whole life, you won't reach but a drop of water here. So there's billions and billions and trillions of molecules there. So, but what happens is that every once in a while, one of the cold atoms will be against the barrier. Okay? And then what happens here, one of the fast one bounces off of it. And what happens when it bounces off of it? Well, it transfers some of its kinetic energy. So this one will slow down. This one in the hot water will slow down a little bit by speeding up the other one. Now this one that's sped up will run into these other molecules and speed them up a little bit. And this will happen countless times. You'll have these collisions, these molecules, these moving molecules are constantly colliding with each other. And they will eventually get to the point where the energy contained in this water will be the same as the energy contained in this water over here, that the average kinetic energy of the molecules will equalize. So, here's what we've got. At the beginning, we had lots of thermal energy here. Thermal energy, or you can call it heat. And that heat got transferred from the hot side to the cold side. Okay? Now, so energy was transferring. Energy was being transferred. And so thermal energy will transfer from hot to cold temperature. Dot, dot, dot. Until what is true? This until only has one out, right? Until they reach thermal equilibrium. Until they reach, they meaning the two different sides here, they until they reach thermal equilibrium, which means they are at what? The same temperature. Okay, now this is a big deal. Thermal energy will transfer from high to low temperature. You'll never see the opposite. You'll never see the cold stuff getting colder and the hot stuff getting hotter. Now, that would conserve energy. You could make the cold stuff colder, extract energy, and make the hot stuff hotter, but that never happens. Not on its own, not unless you get some outside mechanism, or like a refrigerator doing work to make that happen. If you just leave these alone, they will randomize. And thermal energy will transfer from hot to cold temperature. Now, that transfer of energy we call heating. Okay. Now, we've dealt with transfers of energy before. Remember, we had work. Now, what was work? Work was when we did work, right? We applied a force through a displacement, and when we did that, we transferred energy from like your body, like you're pushing on, throwing a baseball. When you do work, when you apply a force to that baseball and you push on it, you're transferring energy from your body as chemical potential energy in your muscles into the kinetic energy of the ball. Or if you're lifting it up, you're adding to its gravitational potential energy. But anyway, you're transferring energy from your body into the ball somehow. And we call that work, or working. Working, or work, is when energy is transferred through a force, right? Remember, we said work is equal to force times displacement. We'll call it delta x times the cosine of the angle between the force and the displacement. But in any case, work was a transfer of energy through a force. And what units did it have? Well, it had newtons times meters, which was a joule. We measured it in joules. Well, now we have heating. Instead of working, we have heating. And heating is when energy is transferred due to a difference in temperature. Okay. Now we have a symbol to represent heating or thermal energy being transferred. And that is the capital letter Q. And you might remember this from chemistry, right? You did this in chemistry, I believe. And if we are transferring thermal energy, well, that means I'm going to have a temperature change. If I transfer thermal energy into something, right, it's going to get either, if I put thermal energy into it, it gets warmer. Or if I take thermal energy out of it, it gets cooler. I mean, let's look right here. This is hot, this is cold. We're going to transfer energy from the hot into the cold like this. Sometimes we show an arrow showing the transfer of energy, and that's going to be Q. Okay, Q, it represents the thermal energy transferred from the hot to the cold until they reach the same temperature. And when they reach the same temperature, energy won't flow anymore. Now, the amount of heat that transfers out of the hot or into the cold depends on how much stuff I have, and it depends on what the temperature change is. Okay? Oh, I'm sorry, off camera. So, in other words, the more mass, this stands for mass, and this stands for temperature. Temperature change. Okay. The more stuff I've got, the more thermal energy I need to transfer it to change its temperature. The bigger the temperature change I want, the more energy I need. And that's it. That's all I can really depend on, except for what material I use. Now, water takes a lot of energy to change its temperature compared to the same amount of, let's say, lead. If you want to change the temperature of lead, if you want to heat it up, it doesn't take a lot of energy, actually, even though lead is really dense. But water, wow. Water, it's really hard to warm water up. You need a lot of energy to raise the temperature of water. Also, when water cools off, it releases a lot of energy. Now, that property of the material to absorb energy, to absorb thermal energy, we give it a symbol called C, and it's called the specific heat capacity. Okay? You might remember this from chemistry. I know this is review for most of you. But what is it? It's a property of that material. It's how much energy you need to raise 1 kilogram of mass of that material by 1 degree Celsius. That's how we define it. In fact, you can solve for it. C is equal to, well, take the amount of heat it took for a given mass to raise its temperature a certain amount. I mean, this is how you solve for the specific heat. How much energy did you need to transfer to it to raise its temperature for a given mass? Now, for water, for liquid water, I'll put C, water. You got to put a lot of energy into it. Let's see, what did I... You have to put 4,180 joules of energy. You know, Q is measured in joules. Now, by the way, I said that work is measured in joules, but heat is a transfer of energy. It's a transfer of thermal energy, so it is also measured in joules as well. Heat is measured in joules. Now, that's if you're a physicist. A lot of chemists or nutritionists, they use calories instead of joules, but it's just a different unit of energy. Okay, and for every kilogram, if you have a kilogram of water, which is like a 1 liter bottle, if you have a 1 liter bottle, that's a kilogram of water, and you want to raise its temperature by just 1 degree Celsius, you need 4,180 joules of energy transferred to it. That's a lot. That's really a lot. So this is the formula for figuring out how much energy is transferred out or into a material. Now, let's say you transfer a material, or you transfer energy into a material. Well, then delta T is going to be positive, isn't it? You're going to have a positive change in temperature. And so therefore, that we say if Q is positive, we're increasing the temperature. But if we take thermal energy away, the final temperature will be lower than the initial temperature, so delta T will be negative, and we'll say that that's negative Q. Negative Q means we're cooling something off. We're taking thermal energy away. Now, let's go back to this drawing. Heat always flows from hot to cold. So heat always flows from high to low temperature. This is a law of nature. It's the second law of thermodynamics. We'll define these laws later. But can you see why? Look at this. Look at this water. If heat were to flow from the cold to the hot, that means these collisions would have to take place in such a way that it would speed up the already fast-moving particles and slow down the slow-moving particles. Now, that's possible if you only have a couple of particles. I mean, it happens occasionally. But the overwhelming odds are that when a fast particle and a slow particle collide, the fast particle will be slowed down a little bit, and the slow particle will be sped up a little bit during a collision. That's how it's usually going to happen. So statistically, these particles are going to slow down, and these particles are going to speed up until they're all going about the same average speed, on average. Okay? Now, let me show you an example of why that is. Okay? Just from a statistics point of view. What if you had a shoebox? Take a shoebox, and you put in a bunch of coins. Okay, and you made them in this nice, neat array. And then you put heads, 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 heads. So everything on the left side is heads, and everything on the right side is tails. Put a T for tails. Okay. Then you put a lid on this box, and you shook it up. And then you open the lid. What's going to happen? What are you going to see? It's going to be totally mixed up, isn't it? It's going to be heads and tails. Well, I mean, if you shake it, it's going to be totally random. You'll have the same number of coins, but the coins are going to be all over. I don't know if I'm drawing the same number or not. But this will be heads, heads, tails, tails, heads, 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 tails, tails, heads, tails, heads, heads, tails, heads, tails. I mean, they're just going to be random, aren't they? Now, you say, oh, okay, well, I don't like this, so I'm going to put the lid back on and I'm going to shake it again. And then you open the lid. Well, if you do this your entire life, if you spent your entire life doing this, you will never open the lid and get this back again, will you? Because this is so improbable. The odds of your coins landing, it's not impossible, but it's so improbable that it just isn't going to happen. Okay? And this has to do with a property called entropy that we're going to talk about later. Now, you can open the lid and force these coins to be, all heads and tails again, but you have to do work to do that. You have to go in and force it to be that way. And that takes energy. That takes your energy to do that. Okay? So, now, if I go to my gases up here, this is having all fast-moving particles over here and all slow-moving particles over here. That's just like having all heads and all tails. And then when I release them and they all run into each other and mix up, they are never going to go back to where they were. And so we say that heat always flows from high temperature to low temperature until they reach thermal equilibrium, which means they're both at the same temperature, and they and so heat's not going to transfer anymore. Okay? Any questions? Let me zoom out before we do an example problem. Okay. Any questions on this? Okay? This is deep stuff, okay? Believe it or not. I mean, actually, it's very intuitive in a way. Right? This is one of those few things in physics that's pretty intuitive. But, I mean, look at this coffee. This coffee will never get warmer because the environment's going to get colder. It's just because the odds of the collisions of molecules ending up with that result are so astronomically low that you could just say it's impossible. Now, it's not impossible, but it is impossible. Okay? I mean, it's just never going to happen. The odds are so low against it that it's just never going to happen. All right. Now, if I can use this idea, and now we're going to do an example problem. Okay, suppose I have, let me zoom back in for this. Okay. Suppose I have a insulated beaker. I'm going to put a beaker right here. And this water is going to be at a certain temperature. So let's say in this beaker I've got half a liter of water, which is 0.5 kilograms. So the mass is 0.5 kilograms of water. And let's say the water starts off at a pretty low temperature. The initial temperature of the water, let's say it's 0 degrees Celsius. Like I had a bunch of ice cubes in there and they just melted, and now the water is at 0 degrees Celsius. And then I put a brick of lead in here. Lead. Okay, now lead, let's suppose this brick of lead has a mass of 4 kilograms. I put 4 kilograms of lead in there. And let's say I just took it out of some boiling water and it cooled off a little bit when I moved it over. So it starts off with a temperature, its initial temperature is 90 degrees Celsius. And then I'm going to put this in a container and put a lid on it. Here's the lid. And I'm going to insulate it from the rest of the environment. So there will be no heat transfer to or from the environment. The water and the lead are isolated. Well, if you wait long enough, what's going to happen? You got cold water in the presence of hot lead in contact. What are they going to do? The lead is going to do what? It's going to give off heat to the water. The random motion of the lead molecules is going to bash into the water molecules and speed the water molecules up, adding to their average kinetic energy, adding to their temperature. So the water is going to get warmer and the lead is going to get cooler. Yes? So we're going to get heat transferring out. There's those arrows again showing the transfer of energy. This represents the heat transferred out. Now, here comes what I want to know is, so this is what's given. What I want to find is, what's the final temperature when they reach thermal equilibrium? At what temperature will they reach? Okay, and that's what I'm going to solve. Well, because this is isolated from the universe, the amount of energy, thermal energy in this system is going to remain constant. Okay, so the lead is going to lose that. Well, let's look at the water. Here's the water. Now, I'm adding heat to the water, so it's going to be positive. So the heat gained by the water will be equal to the heat lost by the lead. Now, when heat is lost, we're taking away heat energy, we're transferring energy out, and so I'm going to put a negative there. That is, the heat gained by the water will be equal to the heat lost by the lead. Okay? Because of conservation of energy. Well, I have an equation for heat transferring into water. Q equals mc delta T. So this is going to be the mass of water. I'll use W for water, times the specific heat for water, times the change in temperature of the water, equals negative because I'm going to extract heat from the lead, or extract thermal energy, the mass of the lead, the specific heat of the lead, times the change in temperature for the lead. Okay, now what I'm going to do, this is messy. And what I'm going to do is I'm going to solve this for the final temperature, and I'm going to leave it in terms of these variables. And I'm going to get an expression for the final temperature. I want you to be able to derive it, but when you're solving problems like this and they ask you for the final temperature, I'll derive an equation that will make it easier to do. Okay, so because this gets messy. This is going to be MWCW, and this is going to be T final minus T initial W. Now, why don't I put T final W on here? Why don't I put the W on there? Because I want to know what the final temperature is when they're in thermal equilibrium, so it's going to be the same for the lead and the water. This final temperature is the same for the lead and the water, so I don't need a subscript. Equals negative mass of the lead, specific heat of the lead, T final minus T initial for the lead. Okay, now what I'm going to do is I'm going to distribute these masses and specific heats into the equation. MW CW T final minus MW CW T initial W. See how long that is? And then equals negative M lead C lead T final. Now minus a negative, right, or negative a minus becomes plus ML CL T initial L. Does everybody understand what I just did there? Okay, now I want to solve this ugly mess for T final. So what I'm going to do, I've already got T final on this side, and I got T final over here. I'm going to move this over to this side, and I'm going to move this over to this side. And when I do that, I get M sub W, C sub W, T final, plus, because I'm going to add it to both sides, the mass of the lead, the specific heat of the lead, times the final temperature of the lead, which is the same as the final temperature of the water, equals, well, I've added this to the other side, so this is the mass of the water, specific heat of the water, times the initial temperature of the water, plus mass of the lead, specific heat of the lead, times the initial temperature of the lead. Almost done. Now I can factor out T final. And so what I'll do, I'll just cheat a little bit to save myself some writing. I'll put T final out here, put this in parentheses, and cancel this out. You see what I did? I just factored out the T final. Now to solve for T final, I just divide both sides by this. and I get the equation that you're going to be allowed to use. Thermal equilibrium problems. T final is equal to the mass of the water, specific heat of the water, times the initial temperature of the water plus ml CO. Okay, I don't really need the parentheses there. This is the physics right here. This is the big idea. That leads us to this equation that you can use to find the final temperature of our system. So now you just got to plug in the numbers. Well, the mass of the water was given to be 0.5 kilograms. The specific heat of water, well, you have to look that up. And in your book on page 279, table 12.9, they list the specific heat capacities of all the materials. Now, if you're doing this at home and you don't have your book or you're too lazy, if you have your computer, just Google what is the specific heat capacity of water, and then feel lucky. And your first hit will give it to you. Or lead, or whatever material you're working with. Or you can look it up in your book. The specific heat capacity for water is 4,180 joules per kilogram degrees Celsius. Now, what was the initial temperature of the water? 0 degrees Celsius. So that whole thing's going to go away. Plus the mass of the lead, the specific heat of lead. Now, if you look that up, it's only 130 joules per kilogram degrees Celsius. Look, lead is easy to heat up compared to water. I need 4,180 joules of energy to heat up 1 kilogram by 1 degree Celsius of water. Lead, I only need 130 joules. Way less. So it's easy to heat up lead. Now, the initial temperature of the lead was 90 degrees. Then you have to divide all of that by the mass of the water times the specific heat of the water plus the mass of the lead times the specific heat capacity of lead Now let's look at everything that cancels out here. The joule kilogram degree Celsius is in every term. So the whole group cancels out. And then we've got mass, 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 and mass. So I've got kilograms in every term, so it cancels out. And then I'm left with degrees Celsius. Now, I'm just going to tell you, do the arithmetic, plug it all into your calculator, and I've already worked this problem out, if I can find it. And it turns out to be 17.9 degrees Celsius. This will be the final temperature. This will be the thermal equilibrium temperature of this system, of this lead, that hot lead in that cold water. They'll reach 17.9 degrees Celsius, and that'll be the final temperature of both of them. And this really works. Any questions? That is all.